Well, welcome. Welcome to Monday. Here we are in our what do you call it? You know, this pandemic, time of pandemic. It's gonna be great. Yeah, we're still here. Yeah, it's very exciting. Okay, so what we're looking at today are parallel and perpendicular lines. Now, these are terms, just looking at lines that are kind of, we're looking at relations in a way. Like, how are these lines connected to each other in a way? And then, obviously, by definition, parallel lines aren't connected because they never do. But what we're going to be looking at are the similarities between the equations, really, of parallel lines and perpendicular lines. Question? No, I didn't do anything. What does it say? Equal. Okay, that's weird. So is that when you try and go, where is it? Down here? And that one. And you've done that, and then it just comes up with saying you can't do it. That's weird. It could be a permissions thing. Try going if you're online, see if you can do it online. Like the browser. I'll pause for a sec. So two lines here. We have two lines. We are essentially looking at the relationship between, or the similarities between the equations with parallel and perpendicular lines. So parallel, we know what parallel means, do we? Hopefully, maybe. So things heading in the same direction, they never cross paths, and they never deviate as well. So two lines of parallel never intersect as they have the same gradient. And that's in the equation. We can tell whether two lines or two equations would be parallel simply by seeing if the gradients are the same. So if now M1 and M2, remember 1s and 2s are just designations of particular things. So we're saying M1 is a gradient for equation 1 and M2 is a gradient for equation 2. We have two lines here on this graph that we can see over on this side. And, oops, okay. And they are, well, I mean, they look like they're parallel, but I can check whether they're parallel or not. If I look at the rise and run of the first one here, the rise is 2, the run is 2, so what's the gradient? 2, yeah, 2 over 2, sorry, yeah. And so the gradient must be 1, because 2 divided by 2 is 1, yeah. And the same deal on this one over here. Now they've gone up by 2, they could have gone 1 as well, a rise of 1 and a run of 1. But both of them have a gradient of 1, not 2, sorry, which means that, sorry? Yes, well, they've gone up by 2, but they've also gone across by 2. Oh, sorry. Well, both. I mean, you can take the point from here to here, and then it's gone up by 4 and across by 4. It doesn't really matter which 2 points you pick to measure your gradient between. It'll be the same because if you're going up by a certain amount, you're going across by a certain amount as well. Yeah. So the gradients are the same, therefore, these lines are parallel. That's really as far as the proof goes there, as far as them being parallel. Perpendicular, on the other hand, is a little more complicated. They cross once and then go further apart, never to see each other again. And the key part there is that where they cross is a 90-degree angle. So there's a very simple way of calculating that. Here, with parallel lines, the two gradients are equal to each other. With perpendicular lines, if you multiply the gradients together, you'd get -1 as a result. But the key thing there is, like, either, that's a way of looking at it. The other way of looking at it is one of them is equal to -1 on the other. So if I have a gradient of 2, let's go with 2, then a perpendicular gradient would be -1 on 2. That's it. If I had a gradient of 5, then my perpendicular would be -1 on 5. If I had a gradient of -2 on 3, a bit more complicated, it's a fraction, and that's, a rise of 2 and a run by 3, then the perpendicular gradient to that would be the opposite of that, so positive, and 3 over 2. We just flip them. So whatever your gradient is, you're flipping it and then making it either negative or positive, depending on just the opposite. Question? No? Doesn't make sense? Oh, it does, okay. Cool. So in this little equation here, I've got this line which is y equals a half x plus 2. And that means it's going up by, a rise of 1 and a run of 2, 1 over 2, rise over run is my gradient of half x. And plus 2, the y-intercept is up there at positive 2. And that's just a nice line just going along there, no big deal. And then I've got this other line cutting through it. And this line here must be of the equation, well, it's passing through the y-axis at 4. So it's got a y-intercept of positive 4, which it does, as you can see here. And the gradient of it must be negative because the other line is positive gradient, and it's negative, negative 2. And 1 over 2 flipped is 2 over 1, which is just 2. And that's it. That's in a nutshell. Perpendicular lines, the gradients are flipped, and then polarity is changed, the sign is changed. So if it's positive, it becomes negative. If it's negative, it becomes positive. And yeah, if it's a whole number, then it's going to be 1 on that number. And if it's a fraction, it's just the fraction flipped upside down. Whereas parallel lines, always the same gradient. And that's it. So the key things to keep note of there. So when lines are perpendicular, the product of their gradients is -1. So if I take any of these combinations here and I multiply them together, the result would always be -1. If I go 2 times a negative a half, well, 2 times a half is 1, but then it's negative, so it's -1. If I go 5 times negative a fifth, well, 5/5 are 1, and that's negative, so -1. And 2/3 times 3 over 2, well, 1.5 times 2/3 ends up being 1 as well, but then it's a negative, so -1. These three equations here, m1, m2 equals -1, and m1 equals -1 on m2, and m2 equals -1 on m1, they're all just versions of the same thing, just been rearranged differently. So if I was going from the first one up here, this m1, m2, all I've done is divide both sides by m2. If I divide the left side of this part here by m2, then I would get m1 equals -1 on m2, which is what I get exactly here. And if I divided it by m1 instead, then I would get this equation. Why is that useful or helpful? Well, sometimes we need to plug some of these things in to figure out the gradient of, whatever it is. So they'll say, you have the equation y equals, 2x minus 5. What is the equation of a parallel line that passes through such and such a point? Well, if we know, I'm getting a little ahead of myself here, but let's just try it anyway. If I have y equals 2x minus 5, and they're saying a parallel line that passes through 3, 7 or something. Well, sorry, yeah, parallel. Well, if I know it's parallel, then I know y minus y1 is going to equal 2 outside of x minus x1. And then I have my point that I can plug into that and get some kind of result. I knew what my m was because I knew that it was parallel to this equation, therefore it has to be a gradient of 2. Same thing, if it was perpendicular, then it would have been just -1 on 2. And that's the same deal. And then I just plug in that point. Okay. So the key notes there, parallel lines always have the same gradient. So m1 is equal to m2. They generally have a different y-intercept. That's really the distinguishing factor there, because they're either going to be above the original equation or below the original equation. And the y-intercept is what really changes whether the function goes up or down in terms of its level. Question? Did that end up working at all? No. It's still not letting you in. Okay. Perpendicular lines, the gradients are inverses of each other. So yeah, I've already stated that. They equal that. And these two things are the same thing, they're just rearranged. Any questions on that? Yes. Any questions on that? No? Okay. Mitch, all good? Okay. Okay, first work example, here we go. Can I move on? Is that fine? Or are people still writing that down? I'll give you a minute. So, continuing on. Shh. Probably should have made everyone quiet before. Okay. So, reading this out. Show that the line with the equation 2y equals 4x minus 9 is parallel to the line with the equation that. How do we prove something's parallel? What's the whole qualification? the gradients have to be the same. Right. So if I rearrange this to have it in what is it, gradient y-intercept form, and this one, gradient y-intercept form, because right now I can't exactly tell if they are the same gradient because I've got 2y equals something, and here I've got 3y and something. So I don't know if they're the same or not. Okay, so step one, rearrange to show the equations in the form of y equals mx plus c, or plus b, whatever you want to call it, and then just check out the gradients. Say, well, clearly m1 is this, and m2 is whatever it is, and if they're the same, m1 equals m2, therefore parallel. Okay, so first equation, I've got 2y equals 4x minus 9, and that's simply a matter of dividing both sides by 2. It's going to give me 2x minus 9 on 2, or 4.5. Yep, sure, that's fine. That's okay. And then I'm going to do the same thing on the other one. Now I've got 3y, hang on, minus 6x. I'm just going to write it out first. It's 5 equals 0. I want to move everything that's not y or involved with y over to the other side. So I'm going to get 3y equals positive 6x because it was negative, and now I've added 6x to both sides, and minus 5. I've subtracted 5 from both sides. Now I want to get y on its own, divide everything by 3. So I get y equals 2x minus 5 on 3. Clearly, let's call this m1 equals 2. And, oops, m2 equals 2. And I can say here, m1 equals m2, therefore parallel. Something like that. Any questions? No? Sure? Okay. Sorry? No. Yeah. Yep, sorry. Yeah, m1 equals m2, therefore the parallel. That's all. That's fine. You can just write it that way. Yep. Yep. What do you mean? As far as if they want? Okay, so if they ask for another, if they ask for an equation that was parallel to something, then all you'd have to do is change the number in the end. So like if I gave you the equation y equals 3x plus 4, and I said, give me another equation that's parallel to that, and you go, well, y equals 3x for starters. That's one. Y equals 3x plus 1 plus 2 plus 3. Technically the same equation you could give as well. Yeah. Yeah, so they're all parallel. But if they then asked, give an equation that has the same gradient but also passes through a certain point, well, then you've got a very specific equation. Yeah, then you're going to have to substitute those points into the thing. Yeah, that's right. Good question. Can I go the next? Oh, we're still writing. Okay. Shh. Okay. Where are you up to? Done. Maya? Nearly there. Okay. Very similar situation. We're just going to show that they're perpendicular. Now, remember, how do we show perpendicular? Well, we're going to have to compare something with the gradients again. Effectively, the easiest way to do it would be to rearrange. Well, this one's already arranged. That's fine. I don't have to rearrange the first one. But the second one, 6y plus 2x plus 12, I'll rearrange that to have y equals something, and then get the gradients, m1 and m2, multiply them together, and if the result is -1, then I know that they are perpendicular. So that works. All right, let's try that. Yeah, you've then proved that they are not perpendicular, and that would be, still. Yeah, that's right. That does happen. Some of them aren't going to be. What? I mean, if your goal was to prove that they were perpendicular, then sure, maybe. But if your goal was to find out whether or not they are perpendicular, then you've still found the result. Okay. So here I'm going to rearrange this one, and this is so 6y equals negative 2x minus 12. So y then equals negative 2x on 6 minus 12 on 6, which is going to be negative x on 3 minus 2. Okay, what's my, sorry, not y1, what's my m value here? m1, let's call it. What's the value of the gradient here? You guys are always fine when I separate. As soon as I put an x on top of, you know, on 3, sorry, gradient. There's a 1 somewhere in the gradient. What is it? 1 over 3? Yeah, almost. What about my negative? Yeah. So my gradient here is just negative 1 over 3. So if I move the x out of it, there'd be a 1 there. Oh, sorry. Okay. No worries. Okay. Let's assuming then the other equation. Well, in fact, I can clearly see. What's the gradient of the other equation? 3. Is negative a third and 3, are they inverses? Kind of, sort of, yeah, with a sign change. Yes, they are, clearly. Okay, anyway, for the other equation, we've got y equals 3x minus 10. What's my gradient? It's blatantly obvious. I'm not trying to trick anyone. Yeah, it's 3. Okay, so clearly that's going to work, but let's test it. Test. So m1, 2. And what does that equal? Well, that equals negative a third times 3. And that equals negative 3 on 3, which clearly equals negative. You do. Any number divided by itself is 1. Well, I hope, well, what if one day? Who knows? We never knew that we needed to know all this corona stuff, and here we are. Oh, okay, cool. Okay, good. You knew that. All right, cool. So negative 1. That's it. So therefore, perpendicular. Actually, what's the perpendicular thing? So parallel is like that. Perpendicular like that. It can be. There's a little square in there. No, right. No, well, sure, why not? I don't know. Yeah. You can just like, yeah, so you can say therefore it's perpendicular. I don't think that's perpendicular. I can't remember what the perpendicular thing is. Oh, perpendicular, I remember now. It's like a T. Oh, my pen stopped working. Okay. We're back to that. Sorry? Yeah, so it's like an upside down T. So this means perpendicular. Yeah, isn't it? Yeah, no, yeah, it's that. And that means parallel. So it's like parallel, perpendicular. So therefore perpendicular. Okay. Any questions about that? David, turn around. Thank you. Why? I mean, that was just silly. You've literally moved like a radius-wise, like 1 meter radius. It's still the same. It's my fault. I blame myself. He is because you turn around constantly. Yeah. Thank you. Yeah, this is therefore perpendicular. Upside down T is perpendicular. Okay. No, that's therefore. Yeah, yeah. Come on, Jess. No, I know, I do. Yeah. Sorry, yeah. Therefore. Yeah, that's right. Yeah, so we can do that for this one up here. So therefore parallel. Therefore parallel. Yay. Okay. I think that's it. I then did question 1, but I don't know what the question 1 was, so we'll leave it. We'll leave it there. That's basically it. Yeah, I don't think it's super complex. But if you have a question, obviously, show me. I'm going to stop the video there. Say bye to our Corona Monday class.